Well, it's my pleasure to introduce the next speaker, who I've had the pleasure to collaborate for quite a while now. And it's a new initiative of this conference to have emerging young leader speakers. So it's my pleasure to introduce Professor Raphaële Clément, who's going to tell us, I think, about sodium battery materials. Thank you, Raphaële. Look forward to it.
Thank you, Gerd, for the introduction. So it's my pleasure to be here. Good afternoon, everybody. And I would like to start by thanking Tony for the kind invitation and the organizers for having me here. It's been a really wonderful experience. I'd like to thank Natalie for all of the hard work in the organization of this event. It's running really smoothly, and it's a lot of work, so I really appreciate that. So today I'm going to talk a little bit about our work on sodium-ion batteries over the last 4 and 5 years. So this is work from my group at UCSB. I'm an assistant professor there since 2018. And the bulk of our work is on batteries. So just as a quick introduction to batteries, you probably all know how a battery works. Briefly, it's composed of 3 main elements, the anode, the cathode, and the electrolytes. Typically, the electrolyte is liquid in current cells. And the way they work is that you have shuttling back and forth of ions. If you have a lithium-ion battery, these will be lithium ions. Today, I'm going to focus on sodium ions. And so you need to have some electrode materials that are able to reversibly insert and extract ions, or we call this intercalation and deintercalation of ions. And your electrolyte needs to be able to shuttle these ions back and forth during charge and discharge. So some of the key metrics of batteries is the energy density of your battery, which is basically the charge that you can store in your electrode. So how many ions can you store reversibly in your cathode and in your anode? We call this the capacity of these electrodes times the cell potential. And so the cell potential is basically the potential difference between ion intercalation into the cathode and into the anode. And then we're also interested in the power of these devices. So it's either the specific power or the power density. And this really measures the rate at which you can charge and discharge a battery. And so it really depends on the ionic and electronic conductivity of your electrodes and the ionic conductivity of your electrolyte. So today I'm going to talk about sodium-ion batteries, and I will talk about the way we try to find better materials to make these batteries more energy dense. And so really the limiting component here is the cathode. And so we're trying to find cathodes with a higher capacity and a higher voltage. But that means that we also need to engineer better electrolytes that are electrochemically stable up to high voltages as well. And we also are interested in safer batteries. As you may have seen in the news, some batteries will blow up, and this is because they have electrolytes that are flammable. So typically, electrolytes have a carbonate solvent that is flammable. We are trying to change that to make those batteries safer. And one of the ways we can do this, is by using solid electrolytes. I'm not very used to the clicker yet. So this talk is going to be in 2 parts. The first part will be on new materials for sodium-ion cathodes, and the second part will be on new materials for sodium-ion solid electrolytes, and I'll focus on the chloride family. So starting with the cathodes here. So first of all, why are we interested in sodium-based batteries? So as you may know, we are moving towards, for instance, renewable energies, and we need to store energy. And so this means that we have an increasing demand in energy storage here. And lithium is the current technology, but we don't have infinite resources in lithium. We're not quite there yet in terms of lithium recycling, so we need to move to more sustainable battery chemistries, and sodium is one of them. Sodium is right below lithium in the periodic table. It's much more abundant than lithium, and it's much more widespread on the Earth's crust. There are some issues with sodium, though. Sodium, if you look at this plot here, you've got the relative size of these ions. Sodium is a larger ion than lithium, so you can imagine that finding electrode materials that can reversibly insert, where you can reversibly insert and extract sodium is going to be a bit more challenging than lithium. Sodium lies above lithium in terms of the redox potential by 0.3 volts, and so this means that the redox potential of sodium batteries will be lowered by about 0.3 volts. So we have typically lower voltage cells with sodium. And it's a little bit heavier than lithium as well. So what this means is that the sodium batteries have a lower energy density, at least by 30% compared to lithium. And so we need to find applications where energy density is less of a importance, and one of them is grid storage. So I will talk a bit about cathodes in this talk, and the reason why we're looking at new materials is because lithium-ion batteries, when you have a lithium-ion cathode that's commercialized, it's typically a layered transition metal oxide. So you have these kind of layered structures where you have layers of transition metals, and in between the layers you can insert and extract lithium. For sodium, that type of material doesn't work as well because you have many phase transitions as you try to extract and reinsert sodium. And these phase transitions are not reversible or only partially reversible. And so really my group is focusing on finding crystal structures that haven't been explored for lithium, don't necessarily work for lithium, but could work for sodium. And so one of these, the family of interest here is transition metal fluorides. And so transition metal fluorides are interesting as cathode materials because fluorine is a very electronegative element, which typically means that it can raise the potential of sodium intercalation and deintercalation. So you can do this at a higher potential, you can have a higher voltage cathode. The problem with transition metal fluorides, and there are actually quite a few problems with transition metal fluorides, one of them is that they're insulating, they are metastable, and oftentimes they'll undergo a conversion reaction rather than an intercalation reaction. So the difference between these two types of reaction processes is that for intercalation, you're not changing the crystal structure, you're simply extracting an ion and reinserting it reversibly. For a conversion reaction, you're breaking bonds, and now your whole material falls apart, and you're making a new material. And these types of reactions are not very reversible. But one of the interesting transition metal fluoride crystal structure is the Weberite crystal structure. And this particular crystal structure is of interest because it has an open framework, so you've got these kind of tunnels where you could imagine that sodium can diffuse through the tunnels, be extracted and reinserted reversibly. And so you can, there is some promise for high sodium intercalation capacities as well as fast ion transport. So we were particularly interested in earth-abundant, sustainable cathode chemistry, so we started to look at this sodium ion fluoride system, Na2Fe2F7, and you might remember from Christine's talk that polymorphism is a thing in material science, and metastability as well. And for this particular material, if you look at the phase diagram that we've computed with first principles, this Weberite structure is actually metastable by about at least 10 MeV per atom above the hull, so it's slightly metastable. The problem is that there are 3 polymorphs to account for, and these 3 polymorphs are within 5 MeV per atom from each other. And so what that suggests is that if we try to make this material, we might be making a mixture of these polymorphs instead of a single polymorph. And the variance, these polymorphs only differ by the stacking of the cation layers. So this is work led by my student, Emily Foley. And so when she did these first principles calculations, she continued by synthesizing the material. So this is a material synthesized by solid state synthesis and mechanochemically assisted. And so this is the synchrotron XRD pattern that you get on the product. And if you do a Rietville refinement of this pattern, you find that the Weberite structure is the dominant phase in the material, in the sample, but it is multiphasic, so you have 3 different polymorphs of this Na2Fe2F7 Weberites. An orthorhombic polymorph, this 2O polymorph, a trigonal polymorph, the 3T, and then a monoclinic polymorph. And then you have some impurity phases. Unsurprisingly, these are the impurity phases that are the ones that are on the hull. So the ones that are thermodynamically stable. So we also looked at this material with NMR. So this is really the expertise of my group, is using solid state NMR to characterize battery materials and to understand their mechanism. So this is a spectrum obtained on this material using sodium as the probe. So here we're probing the local structure around these sodium nuclei in the material. And what we find here is that we have mainly two environments, and we can assign these environments using first principles calculations again, but this is now first principles calculations of paramagnetic NMR properties. And so here we have this main peak is corresponding to the cubic sodium in this material, and then the lower intensity peak is sodium in a bihexagonal pyramidal site. But you can see that there are some shoulders as well. So there seems to be more than 2 sodium sites, which could be explained by the fact that we have more than one polymorph. So we have slightly different environments in these polymorphs too. If you look at the electrochemical properties of this material, what you find is that, so this is the typical voltage curve that we show for battery materials when we test them. The important number here is what we get on discharge. On the first discharge, we get about 125 milliamp hour per gram of capacity, which is okay for a sodium-ion cathode. But the problem is here really the degradation of the performance during the first 50 cycles. So at cycle 50, we are at less than 80 milliamp hour per gram. So there's clearly degradation happening in the material. Another way to look at this is to take the derivative of this curve. So you take the derivative of the capacity with respect to voltage, and you plot it against voltage. And what that tells you is that it tells you about where the redox processes are happening, at what voltages they are happening. And what you can clearly see from this plot here is that the redox processes will evolve with cycle number. So clearly there's something changing in the crystal structure that's leading to these changes in the electrochemistry. So we decided, based on these results, to look a little more in detail at what is going on in our material as we cycle it for, say, 1 cycle or 10 charge-discharge cycles. And so these are synchrotron XRD data and then sodium NMR data shown here. Both of these data sets suggest that our initial Weberite cathode is evolving into a perovskite and a NaFeF3 material. So over time, our Weberite, which was metastable, is starting to evolve into a more stable phase. But beyond what we find experimentally, we were also interested in what does the polymorphism of this material does to the electrochemistry. Is there something we can learn just from first principles about polymorphism and the impact on electrochemistry? And so here we decided to calculate the formation energies of various intermediate points during the charge and the discharge process. So here we're changing the sodium content in our Weberite structure from Na3 to Na0, simulating what we would get if we were to charge and discharge fully this material. And we're doing this for all 3 polymorphs here. So we get these convex holes that Christine talked about in her talk. And what this type of data can give you is a way to calculate the theoretical voltage curve for these materials. And so we wanted to compare these voltage curves that we were obtaining for these 3 polymorphs. And we're comparing this to the experimental data in black here. You'll notice here that we have some big steps in the theoretical curves, and this is because we're not really computing every single composition in this compositional space, and we're not really accounting for temperature effects. But overall, the theoretical data agrees fairly well with the experimental data, but more importantly, what we are seeing here is that the 3 polymorphs are behaving similarly from a thermodynamic standpoint. So we're not really accounting for kinetics here, but thermodynamically, we would expect a fairly similar behavior for all 3 polymorphs, suggesting that polymorphism in this sample may not impact the electrochemistry as much as we think. We do believe, though, that the phase transformation that I discussed is not necessarily an intrinsic problem for this Weberite cathode. It's more the way we are processing the material into a cathode film. And so right now we are trying to improve the way we formulate these cathode films to increase the electronic conductivity of our film, because we really think this is the main problem that's leading to this structural transition. We are also looking at tuning the composition further to stabilize the Weberite structure. And so we're doing here a screening of formation energies of various compositions for Weberites, and to improve the stability. The cyclability, sorry. All right, so in my second part of my talk, I want to focus on this family of sodium, yttrium, zirconium chloride systems, and these are used as solid electrolytes for all solid-state sodium-ion batteries. So the motivation here is that our current state-of-the-art rechargeable batteries typically have this liquid electrolyte, and this is composed of, in our case, a sodium hexafluorophosphate salt, 1 molar concentration dissolved in a carbonate solvent. The problem with these types of electrolytes is that your carbonate solvent is flammable and it has a limited electrochemical stability, so it decomposes at high voltage. The reason why we use such electrolytes is because they have a very high ionic conductivity on the order of 1 to 10 millisiemens per centimeter at room temperature. But as you can notice here, when you dissolve your salts, you have this counterion that's also conducting as you apply an electric field. And in fact, the sodium transference number, which is basically the amount of current that's carried by conduction of sodium ions, is less than 50%. So this transference number is less than 0.5. So what that means is that your counterion is transported better than sodium in this electrolyte, which is not really what you want for a battery. You want to maximize the amount of sodium that you transport across. So you'd want this transference number to be close to 1. So there are ways we can solve some of these issues of liquid electrolytes by moving to an all-solid state battery that has a solid electrolyte instead. One of the things that will be improved is the flammability. These solid electrolytes are not flammable. Some of them have a better electrochemical stability window than liquid electrolytes, especially at high voltage. And they can be very selective to sodium transport. So now you're getting to a transference number much closer to 1. In the solid state, when you have sodium diffusion, you typically have sodium hopping from one site in your crystal structure to the next, and it has to go through this energy barrier, so you really want to find a material that has a low migration barrier for sodium. And so we've been interested in the chloride systems, and this is a plot that's actually coming from the CIDR group. There are 2 properties that we are interested in here: the electrochemical stability window, which is basically the property that's being calculated in this plot here for different solid electrolyte chemistries, sulfides and oxides that are well studied for lithium-ion systems and sodium-ion systems. These ones are not so well studied. And so the chlorides here, as you can see, have a very high electrochemical stability window on the cathode side, so at high voltage, on par with the best oxide systems. But what makes chlorides unique is that they also they contain chlorine anions that are soft. And so this leads to, that imparts ductility to the material. And so now what that means is that if you press your solid electrolyte against your electrode, you'll get a much better interfacial contact between your 2 solid materials, because one of them is ductile. And so this leads to high interfacial ion transport, which is also important when you're considering making an all-solid state battery. These materials are of interest for lithium and for sodium-ion solid electrolytes. So there was a revival of interest since this particular study of lithium yttrium chloride, or LYC. I'll call it LYC today. And so this is work by a group at Panasonic in 2018 that showed that this LYC system, if you make an all-solid state battery out of it and you cycle it against a high-voltage lithium-ion cathode, you'll get a very stable performance for 100 cycles. And you also get a high ionic conductivity with this material on 1 millisiemens per centimeter, so on par with what you would get for a liquid electrolyte. So we decided to explore the sodium version of this material, sodium yttrium chloride, or NYC. And so this is work in collaboration with 2 groups at UC San Diego, the group of Shirley Meng and the group of Xuping Ong. And so Eric here synthesized this NYC material, and what we found was that instead of making the same crystal structure as LYC, which is a rock salt-like structure, and a p-bar3m1 space group, in our case we're making a monoclinic material. And the problem with this is that now we have no sodium vacancies. In the lithium system, we had 2/3 of the lithium sites that were vacant, and that can create, that helps ion transport. In our case, we no longer have these vacancies, and this material is a very poor conductor for that reason. And so we decided to look at possible substituents for yttrium 3+. And if you substitute yttrium 3+ by a higher valence ion, then now you can induce vacancies in your material. You can create those vacancies. And what we found was that if we were to substitute with zirconium, we could potentially form these materials easily. We could synthesize them because the formation energy is not very high above the hull. And our ab initio molecular dynamics simulation suggested that zirconium substitution would increase the sodium transport properties by about 2 orders of magnitude. So the next step was to synthesize these yttrium zirconium chloride systems, and we made a whole series of materials from x equals 0 in this formula to x equal 1. And for all of the ones between 0 and 87% of zirconium substitution, we found that they all form this monoclinic structure. At least this is what we see from X-ray diffraction. So the long-range structure looks like this monoclinic material. And for the N member on the zirconium side, you form this P bar 3M1 structure, which is actually the same as the lithium version, the lithium yttrium chloride version. So now you have some vacancies, as you can see here. And not unsurprisingly, as you start to induce sodium vacancies on the P21 over N lattice, or in this P bar 3M1 structure, you start to increase that conductivity with a maximum at 75% zirconium substitution, which leads to a conductivity on the order of 6×10⁻⁵ Siemens per centimeter, which is okay, but still not great conductivity. So what that means is that if you have a low conductivity, but you have a material that's very stable against a cathode, you might use it as a catholyte. So it's kind of a coating that you would put on the cathode side, where you'd be using a better solid electrolyte, so a solid electrolyte with a higher sodium conduction, on the anode side. And so most of your sodium is transported by your solid electrolyte, and then you have a thin layer of this catholyte just to protect the cathode. And what you find if you make an all-solid-state battery with our catholyte NYZC75, which is basically this material here at 75% zirconium substitution, and if you compare this to the all-solid-state battery without this catholyte, without the catholyte you get initially good performance, but degradation of the performance quite quickly with cycling, whereas with the catholyte you get a much more stable performance. And even after 1,000 cycles, if you cycle this material, this battery at 40 degrees Celsius, you get about 90% capacity retention, which is very impressive. The one thing we couldn't answer in this particular study, and this is the contribution from my group here, my postdoc Pete and Elias worked on the sodium NMR of the whole series of systems. I'm just showing you the N members here. What we really couldn't figure out was the structure. So XRD told us that NYC, the yttrium version, was crystallizing in this monoclinic structure where we would expect 2 sodium sites. But in fact, from NMR, we're seeing a lot more environments. On the NZC side of things, we were expecting, again, 2 sodium environments, and we see a lot more signals in our NMR data, suggesting that we haven't quite figured out what the crystal structure is like. Plus, we found that the conductivity that we were measuring was drastically changing if we changed processing conditions only slightly. And so this led us to perform a follow-up study where we looked a lot more in detail at the relationship between processing, structure, and conduction properties in this family of compounds. And so we synthesized we synthesized basically the 2 N-member phases and the 75% zirconium-doped phase using a first ball milling step and annealing at 500 degrees Celsius, and then 3 different conditions. One of them was slow cooling after the annealing step, so this is what we call the slow cooled sample, or we used a water bath quench, this is the water quench sample, or we used a water bath quench followed by a second ball milling step, and we call this the twice ball milled sample. And so if we start with the zirconium N member, what we find here is that if we slow cool the material, we get a nice phase pure and monophasic material with a P bar 3M1 structure, which is what we had found in the previous study. So clearly here, we have a good handle on phase purity. It's also the ground state structure that we find with DFT, so this makes sense. We're making it in a under thermodynamic conditions. Now if we quench it and ball mill it again, so this is the twice ball milled sample, we now start to have a mixture of phases where our major phase is still the ground state, but now we're forming a minor phase that has the same space group as the other N member, the yttrium N member, so the monoclinic structure here. This structure is 17 MeV per atom above the hole. So it is metastable. The problem is, with these types of broad X-ray diffraction patterns, you can't really quantify the phases. You can see there's a major phase and a minor phase, but you can't really quantify. And so here you go to sodium NMR again. And so these are NMR spectra obtained on the slow-cooled, quenched, and twice-bowl milled samples, and you can clearly see a drastic evolution of the NMR data, suggesting that the crystal structure is changing. And sorry, I have some shading here that is not shown in the slide here, but both of these peaks, this peak and this peak, correspond to the P bar 3M1 structure. You can see that it's present at 96% in the slow-cooled sample. In the quenched sample, it's also the major phase, but if you ball mill the material again, you start forming this other polymorph of NZC. If you now look at the broadening of the peaks for the P bar 3M1 phase, you see that they're much broader in the twice ball milled sample, which may not be surprising. We're basically making a much more disordered version of this P bar 3M1 phase. We believe that there are some stacking faults too that are induced by this ball milling process, because we've seen this in other related systems. But what's important to remember here is understanding what this does to conductivity. And so the conductivity of the slow-cooled phase is very low, but it increases by almost 3 orders of magnitude if you ball mill again. And so the next question was, well, okay, so if the conductivity is going up, is it because we are inducing some more and more disorder in the P bar 3M1 phase, or is it because we are forming this new polymorph of NZC? And so here we did some variable temperature NMR experiments, which I'm not showing here, but basically the main result was that this P21 over N phase is the one that's responsible for conductivity in this material. So now looking at the other N member, NYC, here again we did a slow cooling process, twice ball milled and quenched. So the 3 patterns that we get are shown here. The problem is with these patterns, especially those ones, are very difficult to fit with Reidville refinements, so we decided to simply compare them to the simulated spectra we would get for the 2 polymorphs of NYC that had been reported in the literature. So R bar 3 is one of the structures, and the other structure is the monoclinic P21 over N. What you see here, if you compare the simulated spectrum for the R bar 3 structure, it's very similar to the slow-cooled pattern, suggesting that the slow-cooled sample is mostly this R bar 3 ground state structure that we find with DFT. If now you quench or you ball mill, you see a much more complicated pattern, and you clearly have also some P21 over N polymorph here, which is above the hole. Again, from NMR, what's nice with NMR is that you can quantify, and you can also assign these peaks quite well if you're doing, again, first principles calculations of NMR shifts. Here we have 3 peaks that we can assign to the R bar 3 structure. So these are 3 sodium environments in this structure shown here. And in this particular slow-cooled sample, we have mostly the R bar 3 phase. Now, if we quench or we ball mill, we start to see the second polymorph of NZC appearing. We also have broadening of the peaks corresponding to the R bar 3 phase, suggesting again that we have more disorder in the material. Again, when it comes to conductivity, we have a drastic increase in conductivity going from the slow-cooled to the quenched to the twice-ball milled sample. Still, this is not great conductivity overall, but clearly we are able to modulate it by changing the processing conditions. Unfortunately, we weren't able to do variable temperature NMR on these samples because they evolved very quickly with temperature. So clearly they are not very stable. So just to recap here, so we have 2 N members that are both able to form this P21 over N structure. We can gain some insight into sodium diffusion pathways by using this soft BV software, which allows you to, it's a bit of a crude model, but it still gives you some information about what paths sodium ions could take in this crystal structure. And what you find is that in these 2 crystal structures, you can have the isotropic sodium diffusion. For NZC, you have some sodium vacancies, no sodium vacancies in the case of NYC. So even if you have some pathways, this may not lead to diffusion because of the absence of vacancies. We also have two other polymorphs. For the NZC structure, we have this layered P bar 3M1 structure where you have much more anisotropic diffusion pathways. And for the NYC structure, you have this R bar 3 polymorph, again with anisotropic transport properties. So what we find for NZC, this is the much more conductive polymorph, the P21 over N polymorph. Unfortunately, this is the one where you need high energy conditions to form. So it's only with ball milling that you can form this material. So what that suggests is that if you wanted to make a much better conductor out of this, this material, you'd have to ball mill much more aggressively. For the NYC structure, we believe that this is the polymorph that's able to conduct because this one has no sodium vacancies. And the increase that you see upon ball milling, sorry, going back to this here, the increase that you see in conductivity is likely due to disorder in this R bar 3 phase, as we observe from the broadening of the resonances that are attributed to this R bar 3 phase. So now if we move to the more interesting zirconium-doped system that we found was optimal for conductivity in our previous study. In this material, we actually form the P21 over N monoclinic structure, whether we slow cool, whether we quench, or whether we ball mill it twice. If you look at the NMR data, what you're finding here is we do have an evolution of the distribution of sodium in the different sites in the structure. This is a depiction of results from our first principles calculations of NMR shifts for sodium in prismatic sites in the crystal structure and in octahedral sites. Here we're using a violin plot to depict those, the distribution of these chemical shifts. But what this is telling you is that basically if you have a prismatic sodium, you'd be between -5 and -17 ppm, which is about this range of shifts. So these chemical shifts are likely due to sodium in these prismatic sites. And then if you're in this region, around here, you've got sodium in octahedral sites. So what that suggests is that you have a change in the population of the sodium sites and you're forming, or you're occupying more of the octahedral sites as you ball mill. We wanted to understand a bit better what's the impact of the distribution of sodium in these prismatic and octahedral sites on sodium conductivity, and what is the impact of transition metal disorder in the mixed yttrium-zirconium system. So here we collaborated with the group of Shuping Ong at UCSD, and we looked at diffusion in a model where you have layers of so this is layers of yttrium, and then you've got layers of zirconium alternating. So this is a fairly ordered structure. This is a more mixed structure. And we looked at the impact of these two models on the diffusion properties. And we also looked at different ways of distributing sodium over octahedral and prismatic sites. So here I'm showing you the percentage of octahedral site occupation. Basically what you're seeing is that the circles here are for the layered model. All of them have a lower diffusion coefficient for sodium compared to the mixed system, whereas the distribution of sodium on prismatic and octahedral site doesn't matter very much. So what that's telling you is that mixing transition metals in these materials will improve sodium transport. So with all of this understanding of well, the need to create sodium vacancies in these materials and the need to mix transition metals, we decided to further continue tuning this family of compounds to improve ionic conductivity. And the next step was to form sodium-deficient systems, where we now are tuning the molar ratio of sodium chloride that we have initially, that we have in our synthesis pot, if you want. And we also tune the sample crystallinity. So all of these materials, this is the sodium content now in your material. And you can see that if you take an XRD pattern, these XRD patterns are very broad, suggesting that these materials are not very crystalline. You can also do some sodium NMR on these materials, and you find that you clearly have an evolution of the sodium environments in these materials. You're depopulating octahedral sites, which would have a shift in this region at very low sodium contents. What was interesting, though, is that the conductivity shoots up for these types of more amorphous sodium-deficient phases. And now you can reach conductivities almost millisiemens per centimeter. So on the order of 4 × 10⁻⁴ Siemens per centimeter for the better ones. So for this 0.625 composition, we're now getting to a point where these materials are starting to get to be good solid electrolytes for sodium-ion batteries. The problem is, if you now plot the log of the conductivity versus the inverse temperature, you would expect an Arrhenius behavior if they behave as expected. And this is true for the low temperature corner of this plot. However, if you go to higher temperature, you now start seeing a nonlinear behavior. And so what's going on here is that you're recrystallizing the material. So we had formed these amorphous materials that conduct well at low temperature. But if you start to heat treat those materials or increase the temperature in your electrochemical impedance spectroscopy measurement, now you're starting to recrystallize the material. So they're not very stable. And that recrystallization leads to a loss of performance, a loss of ionic conductivity. So just to recap here, what have we learned? We've learned that in these materials, the processing condition is very important because it will tell you, or it will allow you to control the polymorphs that you form. And we've seen this with NZC and NYC. We also see that ball milling will lead to stacking faults in some of these polymorphs. It increases transition metal disorder in the mixed transition metal system. And in turn, this greater mixing of transition metal species facilitates sodium transport. In the low crystallinity sodium deficient compounds, we can see that now we have a high room temperature sodium conductivity. And what I haven't shown you is that we tested these materials in all solid state batteries, and they perform reasonably well at a rate of C/3. So here you're charging and discharging in about 20 minutes. The caveat is that these solid electrolytes are not very stable. And so you can clearly see this. This is for one of these. This is the best low crystallinity material that we found here. Unfortunately, you can't really see this plot, but what you can clearly see here is a change in the sodium NMR data as you heat treat this material to different temperatures. And again, this is showing you that you're changing the crystal structure with even moderate heat treatments at 50 degrees Celsius. So clearly, the recrystallization process is happening very quickly. And it's affecting the conductivity. So on this, I'd like to thank my group, especially Emily, Vincent, Elias, and Pete, who've done most of the work I've shown you today, and my collaborators, Shirley and Shuiping at UC San Diego. And I thank you for your attention.
Great. Thank you, Raphaële, for a wonderful talk. So we have time for a few questions. Maybe let me start with one while somebody goes up to the microphone. So a lot of, as we now see in the battery field, a lot of interesting materials are ball milled to create interesting compounds. So this is obviously a challenge because it's not a scalable method. Do you see any ways to make these high defect structures, maybe in other ways?
So some of them, yes. These ones, I'm not sure. We haven't really tried that for those chloride systems. For the disordered rock salts, we've shown that they can be made by microwave, which might be more scalable, and clearly it's of industrial interest to scale. But for the chlorides, we haven't really tried anything else so far.
Thank you.
Yeah.
Piero?
Thank you, Raphaële. If you go to slide 10.
Oof. With all my animations?
No, okay.
Maybe
maybe you remember the...
I don't know if
you had
you can try.
dissociated compound.
Oh, there, okay.
Right. So dissociated compound. So do you really see iron 4?
Sorry?
Do you really see iron 4 plus?
Oh, that's a very good question. And I should go back and check what we see here.
Okay.
Yeah.
Sorry.
No, it's good. That's a good question. I'll have to check though. Oops.
Can I ask a question?
Yeah, please, go ahead. One last
Thank
question.
you very much for your talk. Just about the mechanism of diffusion of the sodium inside the electrolyte. Is it vacancy assisted or maybe like substitutional hopping, or what is it like?
It is vacancy assisted. At least that's what we see, because we see a huge increase in sodium diffusion as we create more vacancies in the system. So we haven't we've actually, no, we've done some molecular dynamics simulations, and that shows it too. So yes, it is vacancy
It can be
resistant.
supported theoretically by simulation, AB initio simulation or something.
Yes. Yeah.
Great. Any final questions? Great. Let's thank Raphaële again for a wonderful presentation. Thank you.